I am an avatar organized by Dr. Alemi to present the direct effects multiplicative inference algorithm. This session covers step 1 of the DEMI pipeline. It shows how to determine the temporal order of variables. A fundamental principle of causal reasoning is that causes must precede their effects in time. Without temporal order, we cannot distinguish correlation from causation. We cannot understand direct and mediated effects. DEMI uses a hybrid approach to establish temporal order, drawing on two complementary sources of evidence. The first is conceptual knowledge, derived from domain expertise, clinical logic, and prior literature. The second is empirical evidence, the actual timing patterns observed in population-level data. Let's walk through how DEMI builds a temporal ordering step by step with a simple clinical example. We begin with age, which serves as the anchor variable. Age is fixed at birth. It cannot be caused by any diagnosis or treatment. By definition, age precedes every other variable in the graph, making it the natural starting point for the temporal order. Next, we add treatment. In the clinical timeline, a treatment is prescribed after a patient has already been diagnosed, and the patient's age is known before any clinical encounter takes place. So treatment appears to the right of age in our directed graph, with an arrow indicating that age precedes treatment. We then add complication. Clinically, a complication is an adverse event that arises after a treatment has been administered. This means complication follows treatment in time, and treatment follows age. The graph grows step by step, reflecting the natural causal flow of a clinical episode. Finally, we add death, the terminal outcome. Death, as well as the event we are trying to predict, is always placed last. This four-node directed acyclic graph was organized using the temporal order inherent in the definition of the variables. Now let's look at how DEMI actually computes temporal order from data rather than from clinical definitions. DEMI ranks temporal order of variables by how early they tend to appear in patient histories. For every pair of variables X and Y in our dataset, DEMI extracts 3 counts from its knowledge base: the number of patients where X was recorded before Y, the number of patients where Y was recorded before X, the reverse direction, and third, the number of patients where X was present but Y was never recorded at all. This third count is important because it implies that X has occurred while Y has not yet had a chance to occur, which is additional evidence that X precedes Y. The first evidence count, N before, is straightforward. We scan the population and count every patient where the first recorded timestamp for X is earlier than the first recorded timestamp for Y. NAFTR counts the opposite, patients where Y was recorded before X. These patients are evidence against the direction X precedes Y. They suggest that Y may come first. The pairwise scoring formula will subtract this count, so a large NAFTR weakens the evidence that X precedes Y. The third count, N absent, captures patients where X is present in the record but Y never appears at all. The reasoning here is that if X has already occurred and Y has not yet occurred, then X can only occur prior to Y for this patient. Putting the 3 counts together, the pairwise score for the direction X precedes Y is simply N before plus N absent minus N after. A strongly positive score means X overwhelmingly tends to appear before Y in the population. A score near 0 means the evidence is mixed or symmetric. A negative score means Y tends to precede X. Once we have pairwise scores for every variable pair, the next challenge is to convert those local, 2-variable comparisons into a single global ranking of all variables. This section covers aggregation and sorting, the step that transforms thousands of pairwise votes into one consistent temporal order. To get a global score for a variable I, we sum its pairwise scores against every other variable J in the set. A variable that consistently scores positive against all others will accumulate a large total score, indicating it tends to occur early. A variable that scores with a low or negative total score indicates it tends to occur late. This is analogous to the Copeland scoring method, where candidates are ranked by how many pairwise head-to-head contests they win. Once we have a global score for every variable, we sort them in descending order. Variables with the highest scores occurred earliest across the population. Variables with the lowest scores occurred latest. The outcome variable Y is always forced to the bottom of the list, since DEMI is designed to predict Y from the variables that precede it. This ordered sequence defines the topological ordering of the directed acyclic graph that DEMI uses in step 2. Let's now walk through the actual implementation of this algorithm step by step. The implementation begins by initializing an empty dictionary called scores. This dictionary will hold 1 entry per variable, mapping each variable's integer concept code to its accumulated pairwise score. Starting with an empty dictionary ensures a clean slate before iterating over the variable set. We then enter a loop over every variable in the patient's reported event set. Each iteration will compute the cumulative pairwise score for that variable against all other variables in the knowledge base. Inside the loop, we call getPairs to retrieve the pairwise relationship data for xi from the knowledge base. The retrieved rows contain the 4 co-occurrence counts as well as the temporal precedence counts, n target before code and n code before target. The core directional signal is computed by subtracting n code before target from n target before code for each paired variable. We then sum these sign differences across all paired variables j. The result is the total pairwise score for variable I, a single number summarizing whether it tends to appear early or late relative to all other variables in the set. The aggregated score is stored back into the scores dictionary. After the loop completes, the scores dictionary will contain one entry for every variable, ready to be ranked. The final line of the algorithm sorts the scores dictionary in descending order. Variables with the highest scores are placed first. Every statistical algorithm rests on a set of structural assumptions. Understanding these assumptions is essential for knowing when DEMI's temporal ordering is reliable and when it might need additional validation. This section covers the 3 key theoretical foundations underlying step 1. The first assumption is transitivity. If variable A tends to precede variable B and B tends to precede C, then we assume A also tends to precede C. This is the standard property that allows a set of pairwise comparisons to be summarized as a consistent linear order. In practice, real-world data sometimes produce cycles, situations where A precedes B, B precedes C, but C precedes A. DEMI resolves these cycles by relying on the magnitude of the pairwise scores rather than forcing a strict ordering. The second assumption is asymmetry. Any two variables can both precede and occur after each other. What matters is the frequency of these events. The third assumption is that the temporal ordering is derived from population-level data, not from any individual patient's record. This means the order reflects the typical clinical trajectory seen across thousands of patients. For a given patient, the actual sequence of events may differ from the population norm. Let's close with a summary of what step 1 accomplishes. First, for every pair of variables, we extract 3 counts from the knowledge base: n before, n after, and n absent. Second, we compute a pairwise score using the formula n before plus n absent minus n after, which quantifies the directional evidence for each pair. Third, we aggregate these pairwise scores into a global ranking score for each variable by summing across all partners. And fourth, we sort variables by their global scores in descending order to produce the final temporal ordering.